The instrument that listens to life, the stethoscope. But how to push it to the next level? So, introducing our AI Steth, the next evolution in healthcare. It honors the legacy of the Steth while taking our wellness journey to a whole new level. Imagine getting real-time feedback on your health right from home. This innovative device uses AI to analyze your heart sounds, helping you understand your health better. Plus, it connects seamlessly with your doctor for a more comprehensive picture. And the best part, it keeps getting smarter. The AI Steth will offer personalized insights and connect with your other smart health devices, creating a powerful support system for your well-being. Ready to unlock the future of healthcare? Let's explore the incredible potential of AI Steth and see how it is built. Before we delve deeper, we would like to thank our sponsor Viam. Viam is a cutting-edge platform that simplifies robotics and machine learning development. It offers tools for easy device integration, pre-built machine learning modules, and scalable solutions. Whether it's a small project or a large application, Viam helps bring your ideas to life efficiently and effectively. More about them later in the video. Let's start by training a machine learning model first. So we start with data collection using a public dataset with different heart conditions. Then we pre-process the data and use a technique called transfer learning, where we built on pre-trained models like YAMNet for better performance. YAMNet is an audio event classifier developed by Google, which we adapt for detecting heart diseases. This approach saves time and improves accuracy by leveraging already learned features. After extensive training and testing, our model achieves impressive accuracy, demonstrating its ability to generalize and make reliable predictions on real-world data. Now, it's time to test the model in a real-world setting. For this, we are utilizing the Raspberry Pi 5, a robust and high-performance single-board computer that offers native support for machine learning and seamless integration with Viam. To capture sound from the Steth, we are using the Boya microphone. This omnidirectional microphone captures sound from all directions with equal sensitivity, ensuring comprehensive audio collection. Its flat frequency response faithfully reproduces audio across the entire spectrum, delivering clear and accurate sound quality. Raspberry Pi doesn't come with a built-in audio input, so a sound card is necessary for such purposes. A sound card is a hardware component that facilitates audio input and output on a computer. It typically features a USB interface on one end for connecting to the computer and 3.5mm jacks for microphone and speaker connections on the other end. Now that we have all the required hardware for our real-world testing, let's proceed with the setup. The hardware connection is straightforward. Connect the Boya microphone to the sound card, then plug the sound card into one of the USB ports on the Raspberry Pi 5. Now attach the Steth to the mic. With these connections, our setup is ready for testing. Now let's move on to the software setup. We will begin by installing the Viam server on the Raspberry Pi 5. We started by booting our 32GB SD card with the latest Raspbian OS, ensuring that Wi-Fi details and SSH are properly configured. After booting up the Pi 5, we accessed the terminal via SSH to enable the VNC server. With the VNC server enabled, we can now access the GUI using VNC Viewer. Now let's start setting up the Viam server on Raspberry Pi. We start by logging into the Viam app. If you don't have an account, create one and proceed. After logging in, create a new project, in our case AI Stethoscope. After you create the project, copy and paste these commands from the setup instruction, which will download and install the Viam server on your Raspberry Pi. Once the Viam server starts running on the Raspberry Pi, you can see the device's online status on your dashboard like this. Next, it's time to integrate the machine learning service into our project. We use the TensorFlow CPU service from the model registry, a module of the Viam ML model service that facilitates CPU-based inference on a TensorFlow model. This requires two attributes, the model path and the label path on the Raspberry Pi. We are also using the PubSub module from the model registry. With this service, you can interact with the MQTT brokers to publish and subscribe to topics in our projects. This service requires two compulsory attributes, but we have given 3 as we are using WebSockets instead of default TCP. After saving the config, we need to wait for a few minutes while Viam server installs and starts up the modules. It is quite interesting to watch the logs update as the Viam server sets up everything one by one. After a few minutes of waiting, everything is online and ready to dash. Now we have successfully completed our setup. To make the AI Steth a handheld and a portable device, we thought of using a smaller board that is comparable to RPI 5 in performance. So we opted for Raspberry Pi 02W. The Pi 02W is a compact and affordable single board computer that offers impressive performance in a tiny package. Now it's quite simple, just unplug the SD card from the Pi 5 and plug it in the Pi 02W. But there is a catch. After porting everything from Pi 5 to Pi 02W, we expect everything to work, but it didn't. To optimize performance for less powerful boards like the Pi 0, we converted our TF model to a TF Lite model with a few lines of code. Fortunately, Viam offers native support for TF Lite models through their ML model service. We then removed the TF service and added the TF Lite service, supplying the model paths to complete the setup. Now it's time to add some additional hardware to make the device independent and portable. To power up the Raspberry Pi, we are using a 1800 mAh LiPo battery, which has a nominal voltage of 3.7 volts and can provide up to a maximum of 4.2 volts when fully charged. But the Raspberry Pi operates at 5 volts. To resolve that issue, a voltage boost converter module is used. Apart from the voltage boosting, it can also act as the charge controller for LiPo battery. But this module does not have any standard charging input, so to mitigate that issue, we have used this tiny micro USB breakout module. To save space in this device, we have removed the cases of the USB sound card and will make direct connections between the RPA and the sound card module. We designed a 3D printed enclosure in Fusion 360 to house all the components, making it easy to carry and use. The parts are then 3D printed using PLA filament and will look like this before cohering them together. Now we have all the hardware required, we will start assembling them to form the final device. We have designed a companion app for the AI Stethoscope. The companion app uses MQTT to communicate between the device and app. Currently, we have two modes: analysis mode, in which the heartbeat is analyzed by AI to find any potential diseases, and stream mode, in which the heartbeat sound is streamed to the doctor using the dashboard. The dashboard is designed using HTML, CSS and JS and uses the MQTT JS library to give MQTT capabilities to the dashboard. And there you have it, the AI Stethoscope, a groundbreaking leap towards a smarter, more accessible healthcare. Stay tuned for more innovations like this and don't forget to check out Viam. See you in the next video. Till then, stay healthy.